So I'm so excited that we've got Molly Turko here with us this week. Molly has 13 years of experience in the oil and gas industry and is currently the structural geology expert at Applied Stratigraphix, along with consulting for Turko Tectonics and structural geology. So with her vast experience, it's going to be amazing to have her share some insights with us today on unraveling seismic data for mineral exploration. So thank you so much, Molly. It's wonderful having you.
Well, thank you everybody for joining us today from all over the world. I am really excited to give you this talk, and let's go ahead and get started. So a little bit about myself. Besides what you saw in my bio, I have a structural geology or a PhD in structural geology from the University of Oklahoma, which I am in Oklahoma right now, which is in the central United States. I have a lot of years of experience in the oil and gas industry where we use seismic data very heavily. And in the past several years, I've been pretty big into the mining research and kind of learning all new things and trying to take what I've learned from the oil and gas industry and think about how that can be applied to the mineral industry. I also do teaching for a company called Applied Stratigraphix. They're based out of Denver, and we offer several in-house and online courses. But one of my favorite things that I do is we offer structural geology field courses in Nevada, Oklahoma, and Arkansas. And if you are interested in learning more about those field trips or seeing what I offer or some of the other people offer, you can visit stratigraphyhelp.com. There's a lot of great people that work there. We all kind of have our own expertise. There's stratigraphers, there's a couple other structural geologists. So if you're looking for some fun field trips once you're out of lockdown, then definitely reach out to us at stratigraphyhelp.com. So for today's talk, I'm going to start by discussing seismic data, what it is, how it's acquired, and what that data is telling us. Then I'll discuss a few of the limitations to seismic data and go over some examples. And then one of the things that I really want to do that I'm pretty passionate about is using larger scale structures to basically predict smaller scale structures. So I'll talk a little bit about that. And then I don't have it on the outline, but I do want to quickly go over some resources and also give you some ideas on how you can interpret seismic data when it's really complex. So what is seismic data? Well, I always kind of describe it when I'm talking to people that don't necessarily know what it is. It's kind of like a blurry image of the subsurface. And typically the data is represented in time, but it can be converted to depth, and it can be acquired as 2D or as 3D. So here on the bottom left, you're looking at a cross section of a seismic line, and you'll notice here on the left it's in time. So as the time increases as you go down, that's getting deeper. So within this little 2D cross section, you can see there's several folds at depth. And then here on the right side is an example of 3D seismic data. So with 3D seismic data, that's exactly what you're looking at. Sometimes we call it a 3D seismic cube. It's typically in time, but it gives you essentially a blurry image of the subsurface. So how is seismic data acquired? Well, typically you have an energy source at the surface that can include a vibrator truck, or in the past they've used dynamite, or if Cam was here, we could maybe use a hippo. But we're basically trying to generate sound waves at the surface, and then those propagate down and they'll hit some type of surface such as bedding or fault, and it'll bounce back. And as that sound bounces back, it will go to a listening device, and we call these listening devices receivers. So this is an example of what they might do to collect a 2D line. You can see it's bouncing off some nice bedding layers in the subsurface. And then this is a nice kind of display of what they would do for a 3D seismic survey. They would lay out all of these receivers, so all of these listening devices, there would be some type of vibrator truck over here that essentially kind of vibrates the ground, creating sound waves propagating down into the surface and bouncing back up. These receivers are listening to them, and then there's usually some truck that they're starting to gather that data and think about processing it. So what is the seismic data telling us? Well, since the data is processed in time, it's basically telling us how fast or slow sound waves can travel through the surface. So when you think about how fast a sound wave can travel, you're kind of thinking about the velocity of something or the density of something. So if it's really high density, it can travel really fast through there. If it's a really low density, it might travel a little bit slower. So with that, you really kind of want to think about how changes in density or velocity of a rock will essentially, those changes will result in a reflection to be heard. Now, when you get a sound wave bouncing off a reflection, we usually will call this an impedance contrast. So an impedance is just what you see between something that's maybe low density going into something that's high density. And it's all based on Snell's law. If you want to Google that and look more into those equations, but what you'll see is you're basically looking at sound waves as a function of velocity and density, which is related to both time and depth. So when we talk about an impedance contrast, that can then be converted into what's called a seismic wavelet, which is sometimes called a wiggle. So notice here on this little chart, what you'll see is maybe this is a clay-rich rock, a mud rock, or a shale. Maybe this could be a limestone. So you get an impedance contrast between those two, which then can be processed into a seismic wavelet. And then once you gather those up, you can put those together and start to get that image of the subsurface. You can see how the beds are just slightly folded along here. So something with a big impedance contrast that will have a big amplitude. So think about going from a soft rock like a shale to a limestone. That would cause a big impedance contrast, a big amplitude, so a big seismic wavelet. But you can also get a small impedance contrast. Let's say if you were going into a limestone to a dolomite, both very carbonate-rich rocks, you might still see an impedance contrast, but the difference between the two would result in something that's a smaller amplitude. So with that being said, you can kind of start to think about what might be some causes for a big versus a small impedance contrast. And this was kind of just a quick list that I gathered. So things like lithology. So what's the mineralogy or lithology of the rocks you're looking at? Are you going from something like a very soft rock to a shale that's juxtaposed against a granite, and you're going to get a really big impedance contrast? Well, what if your rocks are homogeneous? What are some other things that might cause an impedance contrast? Things like porosity. So maybe you go from a high porosity zone to a low porosity. Things like fluids. Fluids can change the density and the velocity of the rock, so you might get some impedance contrast there. Faults and fractures. You know, if you're going through a nice simple limestone rock and then you hit a fault plane, that fault plane will then act like something that sound wave can bounce off of, so you might get a little impedance contrast there. And seismic data does have a lot of things that can cause what we typically call artifacts. And I'm not really going to get into the artifacts, but if you're interested in learning more about those, I can send you a reference, or you can, well, you probably won't be able to click on that right there, but I'm more than happy to send you this slide deck if you're interested in it. But there are lots of things that can also cause a seismic signature that's actually not related to the geology. So next I want to talk about some of the limitations of seismic data And I picked kind of 3 subjects that are pretty common. So we can look at the impact of steeply dipping beds, or maybe near vertical faults, or even fractures. I'll discuss seismic resolution. So how thin is too thin? How detailed can seismic data see? And then we'll also look at some examples of what if there's no impedance? So let's start with those steeply dipping beds. So if you think about how the seismic data is processed, you're basically sending a sound or a wave down into the subsurface, and that's going to bounce back off that subsurface to a listening device. Well, whenever you have very steeply dipping beds, a lot of times when that bounces off, that actually can't be heard. If you send a sound wave down and it hits something that's near vertical, that will want to bounce back somewhere where that noise is not heard. So it's actually very difficult to resolve those. And the resolution at what you can gather in your seismic data is really going to depend on the layout of the survey. So back in like the 70s and the 80s, they took a lot of 2D seismic data, and the quality was great for back then, but compared to modern day seismic data, it might not be as good. Whereas now we have 3D seismic, we have tighter spacing, a lot more listening devices, so we can resolve things a little bit better. But this is an example of a 2D seismic line from, I'm not sure when it was required, but it's from a publication from 1998. What I want you to notice is this little area right here. So you can see the reflections. Those reflections represent sedimentary layers, so that's our bedding. Down deeper, we start to get into the granites. So we will talk about that, but you'll notice you don't see those bedding layers in the granites. Notice this area right here. Well, if you didn't know any better, you might want to interpret a fault there. It appears as if those bedding layers are being truncated. So your first thought is, truncation. I must have a fault right there. Well, there was actually a anticlinal structure, and that well had dip meter data. So as they drilled down, what they saw is that there was actually no fault in here. What's actually happening is those beds are just very steeply dipping. So you'll notice now, if I zoom in a little bit, you can see this note on the seismic. It says poorly imaged zone. That corresponds to a steep dip panel. So as that anticline starts to fold over, the dips get a little bit too steep to resolve. So you're not actually seeing that steep dip in the seismic data. And if I go back to that, interpret that dipping panel right here. So all of these beds are dipping, but we can resolve those just fine. But in this old 2D seismic, this geometry here is a little bit too steep to resolve. So another example, and this is an example here in Oklahoma. This was an area where I did my dissertation. So here on the left, this is an interpretation of some very complex seismic data. These are all sedimentary layers, so we see nice bedding in here. Where you see this orange horizon, that's the top of the basement, which is a granite here. So everything above here, we have these nice beds. And you'll notice that as we get into this region here, the seismic data gets a little bit too complex to interpret. So then I've zoomed in a little bit more right here as well. And what you'll notice, you start to get this crisscross pattern. You're starting to get into those artifacts, and a lot of that is being caused by steep beds, as well as near vertical faults cutting through there as well. And these sticks that you see on here, these are all wells that were drilled through this structure. This deep well here has dip meter data, which is not posted on here, just because that would be too much to post. But this has dip meter data, so we actually have a pretty good idea of how those beds are dipping. They are fairly steep, and even though this is in time, it's approximately a 1-to-1 scale. So I don't know how steep that would be, maybe dipping 70, 80 degrees, almost to near vertical up in here. So what you see is that you're not actually able to resolve those steep dips. And this is from a 3D seismic survey. It's fairly modern data. And even with that modern data, you're still not able to resolve those steeply dipping beds in that area where the structure gets very complex. So another limitation to seismic data is the resolution. And seismic resolution, what that means, that's basically describing the ability to distinguish between two features from one another. For example, two thin beds. So if you have two thin beds on top of each other and you're looking at your seismic data, you might be wondering, am I able to resolve those two beds, or will they appear as one bed? Well, in order for seismic data to resolve the beds, the thickness needs to be greater than 1/4 the wavelength. Without getting into all the details of the math and how you can think about that, I kind of just want to throw out some general rules of thumb. So when I think about something that's relatively shallow, a typical seismic resolution is between 10 and 15 meters, or 30 and 50 feet. So the rule of thumb that I always have in my head is that seismic resolution, the smallest, the thinnest thing you can resolve is 40 feet, which falls right in the middle. Once you get deeper, it gets even harder to resolve those thinner beds. So you're thinking of things that are between 20 and 30 meters. And I have a nice picture of an outcrop. This is a sediment-hosted copper mine in Southwest Colorado. You can see, this is approximately 6 meters, approximately 20 feet. And if I were to just generically throw on a seismic wavelet, that might look something like this. So within this mine, there's an area in here, pretty much the top of this bed and deeper. That's where you get really good copper mineralization. And it might be kind of difficult to resolve that if you had only seismic data. So you kind of have to think about, what is your target? How thin is that? And are you going to actually be able to resolve that in the seismic data? And lastly, the other thing that can happen is you get rocks that essentially have no impedance. So this can happen when rocks become very homogeneous. For example, if you're looking at igneous rocks like a granite, and you don't have any dikes or sills or major faults cutting that granite, a lot of times it can appear very homogeneous. So here's an interpreted cross-section down here, and you'll notice you have some reverse faults and then a near vertical strike slip fault here. And where this orange is, that's pretty much our homogeneous granite. This is an area in southern Oklahoma. So what I've done is I've just blown up this area of the seismic data to kind of show you what that looks like. And this is an older 2D seismic line, just FYI. But notice you really don't see a lot of impedance. You don't see a lot of structure. Very difficult to make things out. We did interpret a near vertical fault in this section. Oh, I guess this is outside of this, so you're not going to see it. So never mind, forget that comment there. But these granites do appear very homogeneous in here. The other things that can cause that is maybe if you're looking at salt. So this is a great example of a salt body. Notice you can see all these nice beds around there. Nice impedance contrast between the salt and the sedimentary beds. But within the salt itself, you really don't see much structure at all. Additional examples would include the vertical bed. So if you're projecting a seismic line straight through a vertical bed and you're constantly going through that same unit, just traveling vertically down a limestone, and you don't have anything to bounce back up, that can also create an area where you have no impedance. One more example of that. This is a great paper. I love this example that they throw out there. But you can see here where they've outlined it in black. That's a felsic intrusion. And what you'll notice is that outside of this intruded region, I believe these are sedimentary units that they have shown down here. And you'll notice you do see good impedance. You see these nice reflectors, but where you have that intrusion, you really don't see much impedance within that itself. So that's another example of a very homogeneous intrusion, not really seeing much impedance in there. We'll come back to this example here in a few slides as well. So next I want to talk about how seismic data can be used for mineral exploration. And I like to think about this as a matter of scale. So we'll look at some examples where we want to look at regional seismic data, regional seismic lines, maybe thinking about the district scale. This is great for understanding structural styles. In some cases, you can maybe even see some melts or some basement features. Then we'll look at things that might include the camp scale. So you might be interpreting things on 3D seismic at this scale, mapping fault planes if you're able to see those types of things. And in the prospect scale, depending on how big or small that is, this might be a good spot where instead of using the seismic data, we can use some models or concepts to identify sweet spots, maybe based within a larger seismic data set, like a 3D seismic data set. So I feel like regional 2D seismic lines are great for regional exploration. You can get a pretty good idea of the structural styles at depth. Are you looking at normal faulting? And do these normal faults cut all the way down into the crust, or are they limited to the sedimentary section? And this is just an example, and I kind of liked how clear the seismic data was. You can see a lot of these faults going down to depth. And in some examples, which this is not really the best one, but there are some areas where at the surface, you see a series of normal faults. And then what you see in that deeper seismic data is not all of those faults cut down into the crust. The deeper rooted faults, those are spaced a little bit farther apart. So if you are looking for those faults that cut into the crust, that deeper part, then these regional 2D seismic lines be really helpful. And then there's another area from Canada, and it's funny because there are these YouTube videos, Ore Deposits 101. They're a great series, and this guy Andrew Jackson, he shows this seismic line from the Greenstone Shear Zone. This is in Ontario, Canada. And what you'll notice in this interpreted line is you can see these deep shear zones. And if I show you the uninterpreted version, those still show up really nicely. Like you can still kind of see that thrust fault geometry in that deeper seismic line. And then notice these lighter areas. These lighter areas are what he's identified as melt. And the other really cool thing about this line is there's a mine up here, the Red Lake Mining District. And this is a district, I believe, of, I can't remember. I have another example showing this. I think I do have an example of an iron oxide deposit, but I think that's my next example. Oh, no. Okay, here it is. So the Red Lake mine is one of the largest gold mines in Canada. And it's in Northwest Ontario. Lots of gold there, estimated reserve of 3.23 million. So it's really neat to see how this deep regional seismic line can show some of this structure in the crust, how you can see these shear zones. And then it's nice to see that these faults actually correspond to where they have a pretty large gold mine at the surface. And this area, if you just type it into Google and then do an image search, you can find the website by Golden Goliath, and they show some more seismic data from this area. Now, I think some of these seismic lines are actually the same as this one. They've just flipped it. So this seismic lines runs from south to north, and I believe here it's running from north to south. So it's just been flipped in these. But this is another great area where you can see what some of this deeper seismic data looks at. And I actually kind of prefer this one because what you see is where they've interpreted these faults, they've also annotated on here where you see these mineralizing fluids. And then once again, Red Lake Mine Complex, Dixie Project, and a couple other project areas. So Google this company or Google this mine and then type in seismic data. And it's one of the areas where you can see some great structures at depth in that deep 3D seismic. And then I want to bring this one up one more time because I really didn't talk about the details and minerals. But what you'll see is you have all of these little red and yellow and blue dots, and they're showing areas where you have alteration and then in yellow gold mineralization. And notice that kind of sits where you have this porphyry intrusion. And then the other thing I want to kind of point out to you is notice in the shallow parts of the seismic, you can see some faults cutting down in here. My guess is the surface is somewhere up here, and it's possible these faults can be mapped at the surface. But by having this seismic line, you can see what those faults are doing at depth. You can maybe even see which ones are cutting down into the top of this intrusion, and then which ones might not be as well. So another pretty good example of using that seismic data. And if you're interested in any of these references I'm showing you, feel free to reach out. I'm happy to send you those PDFs. And then one of the things that I always like to refer to is this minerals approach diagram. And whenever you think about the minerals approach, you're basically, it's a way of exploration where you're thinking big picture and then going down to the and then thinking of things like a VMS or a greenstone belt. Instead of thinking of things specific to a certain type of ore deposit, you're thinking more big picture exploration and then going down basically from that district scale to that camp to that prospect scale. So when you think of things at the district scale, you might be thinking of your fluid and your metal source, and as well as the orogenic event. And I like these diagrams by David Rice, if I said his name right. And here you can see, you know, you have this subduction zone, and that's a pretty big scale event that you're looking at. And then you're also going to consider, you know, your large scale structures linking down into the sources. And in here you might be thinking about camp scale. Here I put the letter B to kind of represent that. Those are the larger scale structures linking down into your source. And then at a similar scale, you also want to start thinking about the architecture. So in this case, you're looking at a subduction zone, an oblique subduction zone, which leads to a little bit of strike slip faulting. So that would tie into the architecture. And then once you start to take that down to an even smaller scale, like the prospect, you might want to start to think about the kinematics of individual faults, and if those individual faults might lead to a place where you can put a mine. So it's all about a matter of scale. And at the district scale, some of those regional 2D lines can really be helpful. And sometimes by the time you get down to the prospect scale, you're actually looking at things that are subseismic. So in a couple slides, we'll talk about how you can kind of get around that, how you can use that larger scale seismic data to predict the smaller scales. So I like this seismic line kind of illustrating the camp scale. And the reason I liked it is because when you're at this scale, you really want to do your best to pay attention to fault geometries. And if you are able to take like a 3D seismic survey, you want to make sure you're mapping those fault geometries, because those fault geometries is kind of that next step that I would maybe want to go to, where we can use those geometries to identify subseismic deformation. And one of my favorite references, this is an open access paper just released this year in 2021. It's a great paper where they use a seismic survey. They talk about how the data was acquired, how the data was processed, how the data was interpreted, and then how that relates back to their ore deposits. So this is the example where they were looking at the iron oxides. It's in Sweden. And you can see in this top right image, in the background, you can see kind of a fence diagram of two seismic lines. And then on there, you can see the fault planes that were interpreted. Then in this image, they took out the seismic data, and I can't remember what the colors represent anymore, but eventually that helped them to construct this ore block model, and it's helped them to develop this mine a little bit better and figure out where to go, where are the sweet spots, where are the best places to really kind of just dig in. So I have this paper if you want it, or if you want to Google it, it's open access, and it really has a lot of information about using seismic data from acquisition to processing to interpretation to eventually coming up with that ore body model. Now, once you get down to the prospect scale, sometimes at this scale, you know, you're looking at things that are subseismic. So maybe you're looking at smaller faults or fracture zones that are less than that 40-foot cutoff that I kind of have as a rule of thumb. So one of the things that you can do is, if you have mapped your fault planes, you can start to look at where you can expect fracturing around that faulting. And there's some rules of thumbs that you can do. There's modeling that you can do. But one of the things that I always try to look at is, do I have a perturbed stress field? And can that tell me areas of where I have tension in the rocks versus contraction? And this is going to be really important if your deposit is controlled by structure and by fracturing. So if that's the case for what you're chasing, then having this data set can be very beneficial. So what is a perturbed stress field? Well, just very briefly, if you think about this model here on the right, you can think about this as looking at that in map view. You're looking down on this in map view, and this would represent a left lateral strike slip fault. Well, as this strike slip fault slips down towards the left, that creates a little zone of tension, and that on the opposite side, that creates a little zone of compression. Same thing on this side as well. As that's slipping, that's going to create a quadrant of tension and a quadrant of compression. Well, what I've drawn on here, these black dashed lines, that would essentially represent the orientations of your horizontal stress in the subsurface. So if you're thinking about regional fracture patterns, let's just say that north is up. Essentially, your regional fractures would trend north-south. They like to parallel that maximum horizontal stress orientation. Well, once you start to approach that fault, where you have these little areas of tension, they might start to turn and become a little bit perpendicular to that fault. And then when you're in this little region of compression, they like to parallel that. Well, if you're chasing fractures and you know that your ore deposits are within these tension fractures, these veins, you might want to actually target these quadrants of tension that might lead to enhanced fracturing. So having this kind of model in the back of your head, whether you actually model that with software or you just kind of use that as rules of thumb, this kind of information can be really helpful. Opposite from this, you can think about this as a cross-section view, and you're looking at a normal fault. So as your normal fault slips down, once again, you get this quadrant of tension. And once again, I'm going to pull on one of David Rice's cross sections. So this is a normal fault. And what you see up here in this top quadrant, this is our little tensional quadrant. What you'll notice in his diagram is he interpreted those vein systems, which leads to this nice ore deposit up here. So having some of those kinematic indicators of faults can be really helpful. Especially if you have those fault planes interpreted, you can start to use that information to identify areas of tension versus compression, especially in ore deposits where you want those fractures, you want those veins, and that's what's really controlling that deposit. And then these are just some nice block diagrams showing how the geometry of the fault can lead to areas of tension versus compression. So here's a nice block diagram, but basically what you're looking at is, if this is map view, so if you're looking down on this, if your normal fault is dropping down to the right and you have an outside bend, that can lead to a little area of tension, high extensional strain. That would be good for fracturing if you want that fracturing. Or if you have an inside bend, that can lead to a little zone of compression. And rocks tend to be weaker in tension, stronger in compression. So you might actually get less fracturing here. The same concept can be applied to your cross-sectional views. So once again, if you get this little outside bend, that can lead to a little zone of tension. So you might expect more fracturing. Or if you get a little inside bend here, that can lead to compression. But in order to really understand these zones, you really need to understand your fault geometries, which if you have 3D seismic and you have rocks that allow you to map that, it can be really beneficial information. And in one more slide on kind of those kinematic indicators, you can start to look at areas where you have step overs. So this is an example with strike slip faulting, and there's an old rule of thumb. If you have a right lateral strike slip fault with a right step, that leads to an extensional step, versus if it's a left step or a left bend, that's a little contractional bend. And then with normal faulting, if we want those fractures, a lot of times these relay ramps can be areas where you start to see enhanced fracturing as well. Or depending on your rock type, if you have varying mechanical stratigraphy or rheology, where you have layers that are more brittle versus more ductile, as you get faults developing through there, you can sometimes develop these little pockets as you get the bends in your faults. So those are just a few slides on those little kinematic indicators where you can use those fault geometries to start to estimate where you might have areas of enhanced fracturing. So I have a couple of slides, some advice per se of how you might interpret difficult data, because I know that when you have seismic data, especially within hard rocks, rocks that don't have strong impedance, or maybe you have lots of steeply dipping beds, a complex structure, interpreting that seismic data can become fairly difficult. And even that really deep seismic data, the seismic data that goes down to the crustal level, even the resolution of that can get pretty difficult. So I do have a few kind of bits of advice of how to interpret difficult data. So first, I would suggest you know your geological history, because that can kind of set up some expectations. So as far as structural styles, do you expect to see deep basement shear zones? Do you have old orogenies and you expect to see that in your crust rocks? Or are there old rift faults where you maybe expect to see normal faulting? So by knowing your geologic history, you can set up those expectations. That can also help with orientations. If you know your continents split like this back in the Precambrian, well, maybe that could tell you that you would expect normal faulting at that same orientation. If you have outcrop data nearby, you might start to think about, are you going to be looking at a granite versus a schist? Remember, granites can be very homogeneous. Sometimes it's harder to see that fabric in there unless, of course, it's cut by a dike or a sill or some type of fault. And definitely look for analogs. I'll give you a couple of resources, but definitely look for analogs and other seismic data sets. You know, if I'm looking for shear zones, what do those deep shear zones look like in seismic data? So I can do a Google search and then do an image search and try to figure out what does that geometry look like versus maybe a granite that's been intruded with dikes and sills. What does that look like versus some type of shear faulting? Seismic data is typically presented in time. So you want to kind of play with your scales. My suggestion is to always look at it at a 1-to-1 scale. You don't have to do that all the time, but if you're interpreting structure, at least do that once, because that will help with proper kinematics. There's some rules of thumbs, like Normal faults should be dipping at 60 degrees. Reverse faults should be at 30 degrees. So if you have it at a 1-to-1 scale and you see those low angle faults, that could tell you that that's actually thrust faulting. But if you look at that with high vertical exaggeration, if you stretch your data too much, those low angle faults can then appear very steep. So definitely look at things at a 1-to-1 scale. Whenever you have seismic data within your software, you can always play with the color scales. I actually prefer to look at seismic in black and white. I feel like structure better in black and white. And then just start with the easiest interpretations first. Start with what makes sense with what you see, and then you can kind of start to fill in those areas that become a little bit more difficult. You know, if I interpret a major thrust fault, it really wouldn't make sense for tiny little normal faults up there if that didn't fit with the geologic history. So just start with the easiest things first and then use that to help you fill in the blanks. In this seismic line on the right, this is a great seismic data set. If you go to the website seismicatlas.org, you can see a lot of these seismic images. There's also some great literature on how this was interpreted, and it talks a little bit more about the geologic history. But this comes from an area in Finland, and it's a seismic profile, several of them, and it crosses over a major Paleoproterozoic plate boundary in the Fennoscandian Shield. And I'm probably going to try to butcher some of these words if I talk about them. But the data set is really cool. It's a very deep seismic data set, but the tectonic history includes Paleoproterozoic extension and thrusting. So in some of these data sets where they've the interpretations, you can see what those deep thrust faults look like versus those more shallow normal faults. And there's also some great examples of how it can be, well, how in those interpretations, they kind of show a bit of how it's related to the magmatism as well as the shearing. And then they also kind of talk about how this greenstone belt suffered a thermal overprint. So I start to study these lines and look through the interpretations of this literature reference, I can kind of start to train my eye to recognize those areas. And you'll remember in that other seismic data set, we saw almost a dimming in that seismic data set, and that's what they interpreted as one of those melts. So pretty complex tectonic history. Great reference to start to look at some of this data, and I do have a couple examples. So this kind of goes back in line with how to interpret difficult data. Since I know this came from this reference here, I know a little bit about that tectonic history, and I know a little bit more just from reading the literature. So if I just very quickly, I think I took less than 5 minutes to throw an interpretation on there. I thought what I was seeing through here was maybe one of these like deeper shear zone faults. This is about the region where they've identified the moho. And then what you'll notice is I kind of thought that I was maybe seeing two normal faults up here. It looked like some layers were coming into here and then truncating. So I felt like I saw a fault there, and same thing here as well. So if I had more time, then I would probably try to put a little bit more interpretation on there. But it was kind of just a fun exercise. The good stuff is pretty much what was done by the authors. So I would recommend going and looking at those papers and seeing their interpretations. This was one of their fence diagrams. So you can start to see what the seismic data looks like and then their interpretation. So they have two deep thrust faults interpreted through here. This blue represents a thrust plane as well as this purple. This green is where they interpreted the moho. And then up here, they didn't actually throw an interpretation on this example, but this was where they saw that normal faulting. So kind of just going back between the uninterpreted and the interpreted. So some great resources would definitely include the seismicatlas.org. And you can kind of go into here on the left and add filters. You can add a filter for, you want to see basement structure, you want to see igneous rocks, you want to see normal faulting, you want to see thrust faulting. I love some of the examples of like volcanic sills in there, things like that. And then a lot of times it will give you a seismic line to look at. Some of them are interpreted, some are uninterpreted. And then once you click through, sometimes that will take you to a link where you can actually read about the publication where this was put out there. And if you want to learn more about the seismic line, this one, the one that we were just looking at in Finland, there's actually a YouTube video on it, which is kind of nice. It's only 11 minutes, so not very long. And they discuss some of this deep structure as well as some of the interpretations. And then as I was doing some research for this talk, I really enjoyed this recent paper from 2021, where they use this 3D seismic data set. They talk about the acquisition, the processing, how this data was processed. They talk about the rock layers that they're actually looking at. And then they show you the interpretations and how that was used to construct this ore body model. So another great research, open access. And if you want to email me, I'm happy to send you these links. But just to summarize, it's kind of a funny way to describe seismic data, but seismic reflection data basically represents sound waves being reflected back to a receiver from a source. And what you get is basically like a blurry image of the subsurface. Keep in mind, data is presented in time, which can then be depth converted if velocities are known. It can be acquired in 2D lines as well as 3D. And impedance represents a change in velocity or density, and that is essentially heard by the receiver. That can represent things like rock layers, faults, density changes to the rocks. We saw those examples where they identified those melts. But seismic data resolution, that can be limited. We look at examples of those steeply dipping beds, as well as layers that are just too thin to resolve. And also the struggle with rocks with little to no impedance contrast within them. The deep seismic data, thinking along of 2D regional seismic lines, those can be really helpful to identify those major basement structures such as faults and shear zones, sometimes even melts or changes in the basement fabric. And then 3D seismic, that's really going to help with mapping those fault geometries. And if you are able to map those fault geometries, there are some software programs or some rules of thumbs that you can use that can aid in predicting subseismic faults and fracture trends. And typically, if you are going to use 3D seismic data, I will throw common or maybe better for ore deposits that are hosted within sedimentary rocks. Because you have all of those bedded layers, that usually is much easier to resolve versus something that's very complex, like some type of igneous or metamorphic body. And seismic resolution, that can be limited in hard rocks, I just mentioned, or in rocks with very complex structural geology, just as that one seismic line I showed you from Oklahoma. But when the data is difficult, I would just recommend following those suggestions as a starting point, like know your tectonic history, what structural styles to expect, play with those scales as well as the color scale, and then start with what you see. Start with the things that are most obvious first, and then fill in the blanks later. And with that, I would like to thank you all for joining me, and thank you to Jessica for hosting me as well.
Thank you so much, Molly. That was a great talk.